or a way back?
You have to start from the definition of eccentricity.
Okay, I'll start from here.
Here only, the second point.
So, I'll resume the presentation. So, what we are discussing the definition of moving live loads. So, first, we have discussed that how to define the traffic lanes. That is only we are discussing. So, what we have to do, we have to go this load tab, then this moving load option. Here we have to select the code, that is our India, and then go this traffic line lanes. And when you press this window pop up, here you have to just go to the add, and then this window pop up. So you have to fill all the information here and just press OK. And then this type of definition of track will appear on your model. So what you have to do, you have to ensure that the gravity direction of the model is in the negative z direction in the global coordinate system. I think we have covered up to that. So now the point come the definition of this eccentricity. Here first thing you have to enter the lane name. Then you have to enter this eccentricity. So if your reference point is at the center line of the track, that is in our case. In our case, what I have done is I have created this loading slab here. So I can show that. So I have created this loading slab at the center of the track. So this is my reference point for the moving load definition. So this is the reference point for my live load definition. So I have to put the eccentricity is equal to 0. If our reference point is not same as the center line of the track, then what we have to do is we have to enter the eccentricity which is equal to the distance between the center line of the track and the reference point which we are entering here for the definition of the track. Just make sure that this eccentricity value is the negative toward the left side of the reference points. Generally, the left side in global coordinate system, the y is positive. But here, as is given in the picture, that from the reference point, if we go towards the left, then that is negative direction. And if we go positive, then that is towards the right side of the reference points. So that we have to keep in our mind whenever we are defining this eccentricity. Or the best way is that you just put a dummy loading slab at the center of your track so that this eccentricity is equal to 0, and use that dummy loading slab as a reference point for your moving load definition. So then you have to just add the wheel spacing. I have taken broad gauge, so that is 1.676. Then this span length or CDA. So CDA is coefficient of dynamic argument, which is given in the bridge rules. So either way you enter this. This is as we are performing static live load analysis, so we have to enhance our static live load with coefficient of dynamic augmentation to cater the dynamic effects. So what you can do, either you can enter your CD directly here based on the calculation given in the bridge rules, or you just enter your span length here. So automatically it will calculate the CDA in background. So the best way is just enter here the span length, because there are some corrections on this CDA which has to be applied, which will be demonstrated later. So then wheel load distribution. So in the relay model, it is advised to use the cross beam load distribution here, because we have modeled this grillage. So what we want this load to distribute to these cross beams. So you have to use this cross beams method. If we are using this lane method, then what program will do, it will not distribute the load onto these cross beams, rather it will distribute the load to the ends. So make sure you have to use this cross beam option. And for this cross beam option, you require a cross beam group here. So you need to define a structural group of cross element to transfer the load. And these cross elements are the dummy elements which are placed in the transverse direction. So what you have to do, we have to make a structural group of these cross beams. So I'll show how you can do that. So what you can do, you just go to this tree menu. There tree menu 1 and tree menu 2. You can go to any of them and just go into this group. And here just add new, name it cross beams. So I have already created, so I'll give it cross beam 2. And just to assign the elements to it, just select the transverse elements. So which in my case, this dummy elements, sorry, just these elements. So just activate these, select all and just assign to this. So you can see total 330 nodes and 264 elements are assigned to this cross beam group. So now whenever you are selecting this cross beam command, you have to select this cross beam group here, which is created just now. Then this is for the skewed track, our skewed bridges, so our state bridge. So this is not of our concern. Then moving direction. Moving direction, either you can ask the program to move your vehicle in one direction or in both the direction. So if you just click on forward, then what it will do, it will move the vehicle from start to end only. So the start point is the first reference point and the end point is the last reference point, which is selected here. In the backward, what it will do, it will move the vehicle from end to start. And in both, it will move in both direction, forward as well as in backward directions. So we have to tick this both option, and then just you just select your reference points from here. So I'll show you how to do that. So you just have to go to the load, then moving load, and this traffic line lane. You can see I have already created this lane having the name track. So I'll create another one. This is track underscore 1. So eccentricity is 0. Wheel spacing is 1.676. Then span length is 32.6. And then you just select to start and end point. So what I'll do, I'll just activate this loading slab so that it will easy to select. So what you have to do, you have to just put your cursor in this green box and just select from here till end. And you can see the already, yeah, you will see your definition here. So from 229 number element, it will go up to 599. And eccentricity will take 0 and span is 32.6. And you have just to apply or press OK. So I have already created this. So I'm not applying this. So in this way, you can define your moving load lane. So the next step is the definition of the vehicles. So here 5 load combination of 25-ton loading are considered. So total 5 vehicles are modeled or created here for different load combination. Each vehicle is created. So what you have to do, just in same tab, load, moving load, you have to go in vehicle. Make sure this is India and that all remains same. In vehicles, just go to this add standard. So when you press this new window pop up here, first of all, you have to select the standard name. That is whether you are going for road bridges or railway bridges. So for road bridges, you have to select here IRC, and for railway bridges, you have to select here IRS bridge rules. Then the vehicle load name you can change here. You can just see I have created 5 vehicles: train 1, train 2, train 3, train 4, and train 5. This all 5 vehicles corresponds to 5 different load combinations of 25-ton loading as given in IRS bridge rules. So from here, you have to select the load type, that is broad gauge, 1676 loading, and then 25-ton loading, load combination 1, and thus and then just add this. So in this way, your first vehicle is uh, defined. In the similar way, you have to define all the vehicles. So I'll just demonstrate how to define one vehicle. So what you have to do, this load, moving load, this is moving load code is India. Then go to uh, just go to this vehicle and add standard. So here you have to select the standard name. So that is IRS bridge rules. Then vehicle name, for example, I see train trial. Okay. So here loading type is broad gauge loading, and then it is different type of broad gauge loading are mentioned here. So what we are looking for is 25-ton 2000 loading combination 1. So here you can change your name now, trial, and rest is same. We just need to okay. So you can see here train trial vehicle is defined. So in similar way, you have to define all the five vehicles for different load combinations, and then the part come of moving load cases. So what we have to do for defining the moving load cases, we have to go this moving load case command, and then when you press this, a new window pop up. Here we have to go this add button, and then again a new window pop up. Here you just have to define the load case name and make sure you have to untick this auto live load combination. And then you have just go to the add button. There again a window pop up. Here you just scale factor is 1 for IRS, because only single for this is single lane track and single train is moving, so scale factor is 1. Then moving minimum number of loading lanes and maximum number of loading lanes. So if we are defining two vehicles here, that is rather all the five vehicles here, train 1, train 2, train 3, train 4, train 5 in a single track, then we have to decide this 0 to 1. That is rather the vehicle is present or other one is present. Or if you have only just one train and one track, then you can just select here 1 1, that this vehicle is present because we have only one track. So then you have to select the vehicle which you want to enter and then lane. So I'll demonstrate how to do that. Just go in this moving load cases. So what I have done, I have defined 5 different load cases for different vehicles, and one load case which is combination of all 5 vehicles. So how it will work, I'll just going to demonstrate in a while. So what you have to go, you have just go here, it's add button, and then I'll enter just live load name, which is try, and then this uncheck this auto live load combination. We check this, it automatically create some data there, and then you have to just go this add button, and here you have to select the vehicle. So if I want just one vehicle over one lane, so rather lane is one only. So whether I want to assign all the vehicles in single load case or different vehicles in different load cases, that is up to me. If you want to add only one vehicle in one load case, then what I can do, let me consider that I want train 1 on track 1. So just apply and then okay. So this live load trial is defined here. So how it will work, I'll show here. So let us consider the case 1 in which there is one lane and one train, which is our live load 1 case. In live load 1 case, what I have done is I have just, if I show you, I have just defined one vehicle, train 1 over one track. So you can see here, only one vehicle is over one track. And what in live load all I have done, I have defined all the vehicles, that is from vehicle 1 to vehicle 5, train 1 on lane 1, then train 2, train 3, train 4 and train 5. So you can do in both ways. Both is correct. The second one, that is the all one is more easy to interpret the results. So I'll prefer this live load all, but I'll demonstrate you how this all work in the program. So what it will do, if there is one track and one train on this track, and we have chosen the direction both. So what it will do, it will move this train one in both the direction on this track, that is forward and backward, and then find the critical position of load for different values. That we can check, that I'm going to demonstrate in a while. And then if we'll consider a second case, when we have two trains, just like our live dot all case where we have 5 trains. So instead of 5, if I have 2 trains and that are moving on a single track, so but and both directions, what the program will do, it will move both the vehicles, train 1 and train 2. First train 1 in both the directions, forward backward, train 2 in both the directions, forward and backward. So totally 4 combinations are there, train 1 forward backward, train 2 forward backward, and then it will find the critical position of the load for maximum reaction or bending moments, whatever we want to, that it can give to us. And then I'll present another hypothetical case, not hypothetically, actually it is there in multi-track bridges where we have more than number of one lanes, that is track 1 and track 2. So I'll considering two number of lanes and two vehicles, just for explanation. So what it, and both are directions. So what it will do, it will move the possible combinations of these two vehicles in these two tracks. So possible, what possible combinations are possible, that on track 1 there is vehicle 1, on track 2 also there is vehicle 1, and it will move into both the direction. Or possible combination there, that is no vehicle on the track 1, vehicle 1 on the track 1. In like ways, it can do all the possible cases, and in the both means for all the case it will do forward and backward direction analysis, and that then it will give us the critical position of the load for our response, which is of our interest, example reaction bending moments, etc. So this is how the program will work. So now what you have to do, you have to just define this all. So here I have defined this all 5 load cases just for demonstration. I am just using this live load all combination for the result interpretation, because this live load all will automatically do this 5 combination for me and give the final response, the critical position of the load for all the 5 vehicles moving on the track 1. So for results, what you have to do, you have to just go to the before results. There is one important step in analysis. What you have to do, you have to go this moving load analysis control data command. Here you can play between the accuracy and the computational efforts. For example, it is by default using influence generating points. These influence generating points are the number of reference points on the line element for moving loads and drawing the influence line. So right now what it will do, in one element it will considering 3 different points for generating the influence line. So higher these numbers, reference points, higher will be the accuracy, but then computational time is going to increase. So here you have to decide that how to play between the accuracy and the computational efforts. So by default, it is 3. So I'm keeping just 3 here. And then here you can, for reducing your computational effort, you can just uncheck the results which is not of our interest. So for example, I want only the reaction to locate the position of live load or considering the live load mass. So I'll uncheck all the other this displacement force, all the other quantity I'll just uncheck and just perform the analysis for reaction. Then this definition come, which is important for railway bridges particularly. It use this data for modification of CDA based on the IRS bridge rule. So what it will take, bridge type, steel or RC. So based on this type, it will modify CDA if you have entered the length in the moving load lane definition. But you have if you have entered the CDA directly, then it is not necessary uh, to check to fill these boxes here. But if you are calculating based on the length, then you have to just fill the information here that whether your track is single, double or multiple, sleeper type, whether you are using type 1 or type 2 or some other type which is not mentioned in the bridge rule. Then you have to add the width here, then depth of fill in case of RC bridges. And based on this information, it will modify the CD as per clause 2.4 of IRS bridge rule. So I think I'll demonstrate this how is happening. We just go to the analysis and then to the moving loads control, just here 3, and then this is our steel, all quantities we are going to see. And then a sleeper is our type 1 sleeper, and depth of fill is 0 for RC type of bridges. And then just press OK. And then the next step is there. The next step is perform analysis and result interpretation. So once you have done with this, then the moving load definition is over. Now you have to just perform the analysis. For performing the analysis, you have to just press here and it will perform the analysis. So I have already performed the analysis and I'll just show you the results of the interpret results. Sorry, this is so this is the model. So you just go to the result tab and just there 3 icons are there. So if you want to reaction, you just go to the reaction. If you want deformation, you go to deformation. If you want forces, beam forces, truss forces, that all, then go to the forces tab. So I'll go to this forces tab and then beam forces and moments. So this window will pop up. So what you have to do, results. In this forces tab, you have to go this forces and then beam forces and moments. Then you have to select for which load combination you want to see results. So I am seeing it for live load all, because in the live load all the vehicles are entered in this combination. So it will cover all the possible combinations for different vehicles running on the track. So this the quantity I want to see the movement. So that is a movement in the movement about the y direction, that is about transverse direction. And then if you just check this contour and legend and apply, then this is how it is showing the results. So I'll show here how it is showing. So just my value and you just want to see the legend here and then apply. So these are the results for the moving. Oh, sorry, I have to select here the moving live load. So these are the results for moving live load combinations. So you can see the bending moment maximum at the mid span of the superstructure. You can also see where it is maximum. So for maximum, you have to see the absolute maximum to locate the vehicle. So what you have to do is to locate the vehicle, you have to see in the legend that which value is maximum. Positive maximum is absolute maximum or negative maximum is absolute maximum. So in our case, this positive maximum is absolute maxima. So we have to just note this element number. To locate the position of vehicle for this type of generation of bending moments. So this is the 20th number of element. So just keep in mind. Then also how you can see the position of the load for this moment distribution. Then what you have to do is you can also see the results from here. This tab is there. So from here you can see the table of the results for whole the structure. From there you can also find the maximum value. So I'll just show how you can do this. So you can see here the 20th element is the maximum. So to see which element is this, you can just press here 20. I'll, you can see. Just apply this initial view. Forces. And then just 20. So this is the critical element for moving live load combination. And now we want to locate the position of the vehicle when the maximum bending moment generated at this point. In addition, you can see the results from here. From this tab, you can see the result for all the members. Moving live load all, you have to enter here, and here you can see all the results: axial force, shear force, torsional moment, bending moment, and everything you can see here. And you can just export it. This just you have to copy it and paste in the Excel. So that also you can do. I'm not demonstrating that now. So now what we have to do, we have to locate the position corresponding to this bending moment distribution. So what you have to do, you have to remain in the result tab, just go to the moving load tracer. There is a command called moving load tracer in the software. So when you click on this, a new window pop up here. What you have to do, first you have to select that what is results you want to see. Let us see, I want to see bending moment and forces. Then which load combination you want to see. So this is for moving live load 1. In similar way, you can see for any live load combination. And then key element, which is at which element there are maximum response of that quantity which is of your interest. For example, at 20th element we have for live load 5 we have live load all, we have the maximum bending moment. So just enter here element number 20 and then my, and just then if you apply, then you can see the position of train, which will cause this is position of train 1, because we have selected here live load 1 to create the maximum bending moment here. So if we want to see for the our live load all combination, then just go here, moving results, moving load tracer, then beam forces. Then here you have to just select moving load all, and then key element is 20th element. Then we want to see my, then just apply. So you can see this is the position, critical position for the of the train for generating maximum bending moment at 20th element. So in this way, you can see the position of train for any quantity, minimum, maximum, or in general in any. For example, I want to see for element number 50. So I just entered here 50 and then apply. So this is the loading condition for maximum results at this point, element number 50. So in that way, you can check the position of the train. And also here, you can also see the influence line diagram. If you just uncheck this applied load, then influence line diagrams are clearly visible to us. So this is all about moving load, which I want to discuss here, that how to define the number of lanes, how to define the vehicles, how to define the live load combination, and how it will work. and how to locate the position of the vehicle for maximum response. So this position is important for us when we are going for the response factor analysis, because in the response factor analysis we have to consider three masses. One in the dead load, which is already defined. Second is the SIDL, which is also defined but yet not converted into masses. So dead load also, both actually all the loaded in the program we have to convert into masses. So I'll show in a while that how to convert this into masses. And then you have to take the 50% of live load in the transverse direction only. The mass of the live load, that is 50% mass of the live load in the transverse direction. So which is already discussed by the sir in the morning class, that why we want to consider only 50% in the transverse direction, not in the longitudinal direction and that all. So how to find this 50%? And this 50% mass in the transverse direction is corresponding to that position of vehicle which is giving the maximum reaction. So for this purpose, static moving load analysis is compulsory for us, because we want to locate the position of the live load which is giving us the maximum reaction, and then that position we are using for application of load 50% of the mass of the 50% of live load in the transverse direction. So how to do that, I'm going to discuss that now. So first of all, how to convert the dead load into the masses. So you have just go to the structure tab, then structure type, and when you press this, there is a window pop up. Here just you have to check this, convert self weight into masses, and we want the self weight in converted into all the three directions, x, y, and z. And then mass control, so you can either use a lumped mass or consistent mass. So here consistent mass is more accurate because it automatically consider this off diagonal masses, or rather you can you can use this lumped masses and check this consider off diagonal masses commands, or you can go with consistent mass also. And then how the ISIDL is applied, so you just go to the load tab and then static loads, and then you have to apply a element load, that is a UDL. So this is the starting point of UDL and this is the end point. So you are just enter the X values here and the intensity of load. I am not going to discuss the calculation here. The calculation are easier. You are just multiply the density with the area to get the UDL of the respective SIDL, and then you have to convert this SIDL into masses. So here one tab is given there, load to masses. You have to click on that tab, then a new window pop up where you can enter here the direction in which direction you want to enter, you want to convert the mass, this load mass, in which direction you want to convert. So as ideal, I want in all the three directions, x, y, and z. Then this load case you have to select here that as ideal, and if you add and apply, then it is automatically converted into masses. So I'll show how to do that in the program. Just open trial. So that is the trial model. So what you have to do for dead load, just go to the structure type, and just check this convert self weight to masses. And then for SIDL, just go to the load, static loads, and then in the element load tab, you have just apply here the value of SIDL and just apply over the bridge. And then for load to masses, here the command is given there, load to masses. So just go there, select the direction, select the vehicle as ideal, just add. So that is already there, and then OK. So when you press OK, so you will see the locations where it will put the SIDL into masses. So the location at which the SIDL are defined as a UDL, that is converted into masses at the same location. And then the next part is the definition of mass for the live load in the transverse direction. So for that, what you have to do, we have already performed the static moving load analysis. So what you have to do, you have just go to the result and then locate the position of maximum reaction. So go to the result and moving load tracer. Before that, you have to locate the position which is giving maximum reaction. So what I'll do, I'll just demonstrate that how to use that. This is the model. Sorry. Just go the results, then forces. Sorry, we have to go to the reaction, then moving live load. All I'm checking, all I am using, then reaction in the Z direction, then just apply. So you can see it will giving us the maximum reaction at node number 459. So if you look at this 459, so that is at the pair base, it is giving the maximum reaction. Then what we have to do, you have just go this moving load tracer and the reaction. Here you have to enter just 459 for live load L, and then we want to see FZ and thus apply. So this is the position of the train which is giving the maximum reaction at this point. So now switch to the direction. Sorry. So now this is the position. We have find it the reaction and then enter the here the key locations. And then what we have to do, we have to go this right max min load file. Correctly so here. To this right is max min load static max moving load converted to static loads. So what it will do, it will convert this position into static loads. What you have to do, you just uncheck this and you have to save this file as giving some name. So I'll give it live load in transfers. I'll be trans only. Then just press OK. So a new, so it will fail to open. So a new window pop up. What you have to do, you have to just copy all this data. Just copy it and go to tools. In tools, you have to go this MCT command cell. And here you have just type beam load and just paste your value here. And then if you run, you will find a new static load case defined here. Static load case 3 MV all live load for node number 459. So I'll just show in the presentation. So what you have to do, go to tools, MCT command cell, and then just press here start beam load, and then paste your value here. And then if you run, you will find this static load defined by the program for MV max live load for the maximum reaction at FZ at the node number 459. So this UDL is defined by the program. Now what you have to do, you have to just convert this load into masses and make sure you have to just convert this load into transverse direction only, and with 0.5 scale factor, that is only 50% have to consider in the y direction. And how to do that, I'll demonstrate in a while, because there is a limitation of the program that it convert the load into masses only in single direction, either in y direction or in xyz direction. So I'll demonstrate that in a while. Then the next term is the definition of the stiffness, because IRC SP114 asks to consider 0.75 times of the gross moment of inertia for the section which is going to deform in the response spectrum cases. So that is the peer section. For that, we want to reduce the moment of inertia. So we have to consider only 75% of the gross moment of inertia to be effective in the response spectrum load case for the peer. So for that, what we have to do, we have to first create a boundary group named as peer. Then go to the properties. In the section manager, you will find a stiffness tab. There you have to go to the boundary group which is already defined here and assign the stiffness 0.75 to that group. I'll show how to do that. So what you have to do, you have to just go to the properties, then section manager. Before that, you have to just create a boundary group. For example, I have created this peer here, this peer as a boundary group. Then just go to the properties, section manager, then stiffness. Then just take any one section here. For example, I am taking this. I'll define new boundary group, so that will be easy. I'll just define here underscore 1. So what you have to do, you have to go to properties, section manager, then stiffness. Then here just tick one of the peer element, because we want to decrease the stiffness only in the peer and only for the response spectrum load case, not for response spectrum and time still load case, not for the static moving load or other cases. So just go there and then select the boundary group which is just defined. So I'll select peer 1 and then just enter the stiffness here and then add. So stiffness about y and z direction. So note these y, and z are written in the small letters, so that are about the local axis. So that you have to enter here and then close and then go to the, and then you have to, and I'll state here. Then you have to go to the analysis and boundary change assignment. There you have to select the section stiffness scale factor. What you have to do, you have to go to the analysis, then boundary change assignment. Then here you have to select this section stiffness scale factor and then select the boundary group for which you have defined the reduced stiffness. So that is peer, and then you can name it. For example, I can name it that section peer underscore 1 and peer 1. So just add this, and for this here, the load case and analysis, this time history, response spectrum or eigenvalue analysis, you have to just use this cracked stiffness and just apply. So it will take the cracked stiffness only for response spectrum time case, eigenvalue analysis and time history analysis. So that you have to make sure. And then then we have come to the definition of response spectrum. So for defining the response spectrum, you just have to go to this load tab and then this dynamic load option, and then there is a option RS functions. You have to just click this function and a new window pop up. In this tab, what you have to do, you have to just go this to this add button, just press this, and again a new window pop up. So here you have to define your response spectrum function which you are going to apply on the bridge. So currently I'm analyzing for zone 5 and soil type 1. So what you have to do, you have to just go here, design spectrum, and then a window pop up which will ask which code you want to use. So I have used IS 1893 for zone 5, soil 1, damping ratio 5%, and just note that I have used I is equal to 1 and R is equal to 1. So when you are when final forces are with us, we have to just multiply them with I by R. So this response factor is generated. So you can see here at 0 it is 0.18. So Z for zone 5 is 0.36 and it is giving us 0.18. So that is, it is giving us for Z by 2, that is for dB level of earthquake. And here we have to multiply with 1.5 scale factor. Uh, so here the design spectra is used for dB, Z by 2 multiplied by 1.5. So Z by 2 multiplied by 1.5 is dB. Then zone 5 and soil type 1. So make sure that if this load factor 1.5 is taken here, then in the load combination is just 1.5 time dead load and earthquake. Here no load combination have to use, because this load combination factor is used as a scale factor here. Or other way, what you can do, you can just use the scale factor as 1 and you can multiply later this 1.5 as a load factor. So you have to multiply either in the load combination, either in the definition. This is not to be multiplied 2 times. So that we have to keep in the mind. And then I'll just show how you can do that. So what you have to do, you have to load dynamic loads, then response spectrum function, just go to add this design spectrum. I have to just add here IS 1893, then zone 5, soil type 1, damping ratio is 5%, impoundance factor is 1, and then the response reduction factor is 1, and then just press OK. So this is generated, and then use the response factor of 1.5. And then if you apply, then it will generate here. Then now we have to define the load cases for the response factor. For that, we have to go this load, dynamic load and RS load cases. So here, when you press this RS load cases, a new window pop up. Here you can just create different load cases. For example, for response factor in X direction, you just enter RSX here, load name, and then direction XY. And this excitation angle is 0, means it is in the global X direction. And from here, if you enter the value, it will move anti-clockwise. So for Y direction, you have to just enter here 90, and then this mode combination rule. So you can select mode combination rule from here. So I'm just using CQC. For more detail, you can go to this clause number 7.7.5.3 of 1893 about this mode combination rules. And then the function which we have just created, yes, we have to select that and just add this. So what I'll do, I'll just show you how to do that. So what you have to do, you have to just go this RS load cases. For example, RSX1, just this, I'm applying in the X direction only. So direction XY, excitation angle 0. And then this model combination rule is CQC. And then just check this function and add. Similarly, for Y direction, what you have to do, you have to just enter this excitation angle 90 and change the load case name to RSY1 and just add. In the similar way, you can do for the Z direction. For Z direction, similar function is used just by scale factor of 2 by 3. So 2 by 3rd response factor is considered in the vertical direction, and then you have to just analyze it. So now the loading and definition part is over. Now we are just going to discuss the results. So first of all, the results of free vibration analysis, that is eigenvalue analysis, is discussed here. So this is important to perform free vibration analysis, because we want to know how many modes to be considered in the response spectrum analysis or model time history analysis, because we want to consider the number of modes up to the mode which give 90% mass participation in either direction. So from the model analysis, the TS is the shortest fundamental period and TL is the longest fundamental period. So TS is the shortest period in any of the horizontal direction, either in X, that is in longitudinal or transverse, and TL is the longer one. So here some catch is there in the software that it only convert the load to masses in single direction. And what we want is, we want that S ideal is converted into X, Y, Z, X, Y, and Z directions for X and Z direction analysis. For response spectrum in X direction, we just want dead load and S ideal in all the three, rather in X direction. For Z direction, we want dead load and S ideal in Z direction. And for Y direction, we want S ideal in Y direction, dead load in Y direction, and then additional 50% live load in Y direction. So that is not possible to do in the single model in the software. So what I have done is, I have created two different models. In first model, the S ideal is only applied, only S ideal is applied in X, Y, and Z direction, and then this model is used to analyze for X and Z direction. And then a different model, that is model 2, is created, in which the S ideal and 50% of live load is converted into X, Y, and Z in all the three directions. And this model is used for the analysis in the Y direction. So this is one way to do this. And the second way to do this is, you just use the nodal mass command. So the live load, the static live load which we have copied from the movie load tracer, what you have to do, you have to just define any nodal mass, very small mass at any load, any node, to get a nodal mass table. Then just go to the query, and from there you can open the mass summary table and copy the mass in the y direction. But note that when you are doing this, only S ideal, 50% S ideal is applied in the transverse direction. And if you copy that mass and just paste that in nodal mass table, then it can also apply the nodal mass in the y direction at the same location at which the live load is there. So this second one is little bit confusing, and it is not recommended for the new users. I just demonstrate to you how to do that, and I am going ahead with these two different models. So I just demonstrate how I have done that. Which model is that? Trial. This is the model in which I have done that. So what I have done, I'll just show in the trial model, so that is easy for you. Just what you have to do is, I have to open this, just go to the load, static load, and nodal mass, and just add a very small number of mass to any superstructure node, most preferably to the node where the live load is there. This is applied, and then you can see a nodal mass table is generated here. You can see that table by that. And then what you have to do, you have to perform the analysis again, and just go to the query, this mass summary table. Oh, for that you need not perform analysis. For that you need to perform analysis again, because you just have to convert the load to masses now. Load to masses, load, static load to masses only for the live load, and only in 50% and in y direction, and just add and delete that. So you can see this is the critical position of load, and just go to the query, mass summary table, and you can see now x direction, no load to masses is there, just load to masses in y direction. So this is the load to masses for live load position. What you have to do is, So just copy this node number and this load to masses and just paste in this nodal mass table, and then you have to make sure you have to copy all of this. So I have done that in a different model. I'll show that to you. This. So here I have done. I'll just show you that. So this is the critical position of the live load. So here I have considered it as a nodal mass. So if analyze this model, so this will give you correct results in both x, y, and z direction. But for demonstration here, I have just used two different models. In model 1, SI is converted into x, y, and z direction, and in model 2, SI is converted into x, y, and z direction, and 50% live load is also converted, and this is used for y direction analysis. So you have to make sure that which process you are using, and then according to that you have to interpret the results. And this is the free vibration analysis for first period in the transverse direction. So this is taken from the model number 2, and here the mass participation in the first mode is 74.81%. So you can see from here also that almost 75% mass, this is rigid, this is rigid, this is not moving, and almost 75% mass is moving. So period is 0.48 second. So this is the first period in the transverse direction, which is because the period in the longitudinal direction is less than that, so this is the TL, longest period in the fundamental direction. And then if this is the first mode in the longitudinal direction, so you can see here only 53.13 mass is participating. So this can also be verified visually that only one superstructure and half of the pair, that only 50% mass is vibrating, and rest 50%, that this span and pair bottom is almost fixed at its own position. So only 53 mass is participating in the longitudinal direction. So it has a period of 0.28 seconds. So this is the TS, shortest fundamental period, and the previous one, that is TL. So make sure these results are from model number 1, in which SI is converted into X, Y, and Z direction. And on the similar line, there is a mode shift for the Z direction. So that are also taken from the model 1. So, and you can see only 43%, that is only one superstructure is vibrating at a time. You can visually verify this. This is the period in the Z direction. Then the next thing is from the mass participation. So we have to take the number of modes up to that mode, which gives the 90% mass participation in the respective direction which is of interest. So in model 1, the axis of the interest or analysis are done in the X and Z direction. So the interest directions are X and Z. So we want the 90% mass participation in X and Z direction. So you can see in the 31 modes, we are having 91 mass participation in the X direction. But in the Z direction, we have only 62.87 mass participation. So this is because this is less than 90%, but we are going ahead with this because if we see the mode shift in the Z direction. So by seeing, you will confirm that only superstructure is vibrating in the Z direction. This pier and pier cap are axially very rigid. So this 62% which it is giving, it is out of superstructure mass only, not out of the 100%. It is out of superstructure mass only. So what we have to do, you have to we can go with this. What we have to do is we have analyzed. We have to analyze if we are analyzing for this condition only. So what we have to do, we have to enhance our results by adding the forces corresponding to pier and pier cap corresponding to Z by 2 into 1.5 factor by considering the mass of the pier and pier cap. Or alternatively, what we can do is we can apply the missing mass correction in the Z direction, and we can analyze then the forces are in the actual Z direction. So either way we can do. So this is the mass participation in the second model, which is used to analyze for the Y direction. So here in the 25 modes, we are getting 90%. So for this model, I am using 25 number of modes. So then it almost we comes to the end of the presentation. Now just the result interpretation is there. So first the results are shown for the base shear. So in the X direction, the base shear is, I'll just show in the model, easy to understand there. This is for model 2. This is probably model 1. This is for model 1. So I think some modification are made here. It is difficult to rerun it. What I'll do, I'll explain for model 2, that is for Y direction. So in Y direction, we can see in the Y direction is in transverse direction. The shear which we have to check is also in the Y direction. So in Y direction means local and global Y direction are in the same direction. So we have to check just in FY direction. But for X direction, this is the X direction, that is longitudinal direction. Here the shear is also in this X direction. So this X direction is locally the Z direction. And when you see the results, go to the results and forces. Here these subscripts are written in the small letter. So that are along the local element axis. So if you want to shear, check the shear in the X direction. If you want to check the shear for response spectrum in X direction, what you have to check is small f, small z. That is the shear force in the X direction. This small z means the X in the global coordinate system. So this is the shear force for response spectrum X, and then this is for response spectrum in Y direction. So how to check that? I'll show here. You just in the similar way in which we have checked the results for the moving load analysis, the similar is there. You have just select the RS Y here, then F5 we want, then contour and legend we want. So it will give the shear force in the Y direction. In the similar way, you can get, check the bending moment in the X direction. So bending moment in X direction is about the transverse axis, that is the Y axis. So this is the results, and for the response factor in Y direction, the bending moment is about X, global X direction, that is local Z direction. So that you have to make sure that you have checking what value software is giving is about the local axis. So that you have to keep in your mind when displaying these results. And what you can do, you can also plot the table from here for which any of the load case for which you want to see the results. So I think that is all from my side. Thank you.
Thank you, Mohit. It was a very good demonstration. Given the time we lost to internet connection, you managed to finish it well within time. So, can we take up questions now?
Yes, sir. Yes.
If I remember, there was a question before we lost connection regarding the stiffness that you are defining in the bearing length. The value that you are taking is around 10 to the power 8. So, is there a clause or some reference, or it is something that is defined like that?
So there is no clause like that, whether we have to take 10 to the power 8 or 10 to the power 6. That is on our judgment. We have to take a large number so that it will fix in that direction. So you can take either 10 to the power 6 or 10 to the power 8 or 10 to the power 10, but higher number is recommended. So that you have to take.
Let me add here. Actually, the idea is that it should be sufficiently rigid At the same time, it should not be too rigid. So if it is too rigid, then if we give too high a value, then numerical instability will come. So generally what we do, we calculate the stiffness of some other elements, the typical elements. For example, in this case, it may be pier. So we calculate the pier stiffness, and 100 to 1000 times of the pier stiffness is adequate. So in that range, we can assign, and it is based on experience. I mean, that's the norm in finite element. When we have to fix a particular direction, we can assign these stiffnesses.
Okay. Thank you, sir. Thank you, ma'am. Mr. Abhishek is suggesting something regarding his experience on modeling of composite section girder bridges. So he's saying that there is some bug in MIDAS and it does not calculate IXX correctly. You have to manually input the correct stiffness scaling factor. So is it
Okay, so
like
we
that?
can take a note of that and check in our calculation. Okay, and we can check and verify. So for some composite section, let's make a composite simply supported beam, calculate its deflection at the center, what should be theoretically, and what we are getting from the software, and cross check whether it is considering correctly or not.
Okay. And then Sugandha is asking how is mode 1 bracket longitudinal practical? I think so. What she is asking is mode 1 in the transverse direction. How is it practical?
The question is not very clear. What is the question exactly? Can you read them? How the mode 1?
Sir, how is mode 1 longitudinal is practical? I think so. She is asking about the transverse movement. Mode 1 we are getting as transverse in transfer direction, right?
So see, whichever direction is having longer period, that will become the first mode. So and the period will depend upon stiffness and mass. So we have to compare the stiffness and mass in the two directions, and whichever is having the highest ratio of mass to stiffness, that will become the first mode. So it is simply that. So in the longitudinal direction and transverse direction, the distribution of mass is different. If it is a circular pier, then stiffness will be more or less same, except that in the transverse direction, the length, the effective length of the pier will be more because the mass will be lumped at different heights. So taking those into account, we can manually calculate, and it will depend upon the bearing arrangement. So any of the two modes can be the first mode, depending on whichever is having a higher M by K ratio.
Okay, sir. Viol is asking what will I do if mass participation is less than 90%?
We discussed in the morning that you have to go for time history analysis or use missing mass correction. You have to first identify why you are not able to get 90%. So is there any rigid portion which is not vibrating? So then you can apply the correction for that or go for time history analysis.
So Sugandha is clarifying the question. How is the connection between two spans separating in the particular mode in the longitudinal line?
Sorry, can you read again? How the expansion
How is
joint?
the connection? How is the connection between two spans is separating in the longitudinal direction?
So there is no connection between the two spans, if I understand. So one span is on roller, the other span is on rocker. So the rocker span will move along with the pier, whereas the rocker span can move relative to the pier. So the two spans are not connected among themselves. Those are free to move with respect to each other. I hope I have understood the question correctly. Perhaps she meant that, or she was having something else in mind. I don't know.
Sir Bharat is asking, do we need to check seismic forces in construction stage analysis here as it is the interaction of concrete deck and steel girder?
Yes, so the codes provide the mm, load factors. So we consider a lower level of earthquake during the construction. So we can take as per the relevant code.
Okay. That is all that I can see in the chat box. If participants have any more questions, they can put it in the chat box as well. We
Okay,
have
so
received a lot of queries regarding the copies of the presentation. So, we
yes, so
will
copy
try
of the
to
presentation in PDF will be made available. No problem with that,
along with the recording.
as well as the recording. So that recording link for recording and PDF copies of the presentations will be shared with all the participants. And in any case, those will be available on our channel in public domain. So anybody can see from there, even if they are not registered for this course, though they can also see those.
We have a new question. While modeling elastomeric bearing in our project, we apply stiffness of elastic link. The stiffness in two horizontal direction are in the range of 2000 kilonewton per meter. While we run the response spectrum analysis, base shear reduces due to less bearing stiffness. I want to know the process of modeling the elastomeric bearing.
Actually, we will talk about this tomorrow. There appears to be some confusion regarding elastomeric bearings. Elastomeric bearings are used in different ways in the bridges. So when you are using elastomeric bearings without any stopper, it acts like a base isolation. So when it is acting like a base isolation, so then in that case the period elongates, and due to elongated period, the base shear will reduce. Now, elastomeric bearing can be used as base isolation. It can also be used just as a bearing. In this case, I mean, when we are using those as bearings, we have to provide some device, either a stopper or a STU or something, which will prevent the horizontal movement at the bearing level. So it will connect the superstructure with the substructure, bypassing the bearing. Later load will be transferred through that, and the role of the bearing will be only to accommodate rotation at one end and rotation and translation at the other end. So these two different applications are there. In the first case, when you are modeling, so on the pier to which it is connected, means where the stoppers are provided, it will be connected rigidly in horizontal direction. You will not provide any flexibility or any possible movement with the stiffness in the horizontal direction. Then the period will come, what is coming because of the deformation of the pier. Otherwise, if you are not providing those stoppers, you are modeling the elastomeric bearing, then the flexibility of the bearing will come into picture and it will start acting like a base isolation. There is no harm in that also. But when you are using elastomeric bearings as base isolation, then there are certain requirements which these base isolation bearings have to follow.
Okay, so that was all in the questions. So should we close today's session?
I think we can close today's session, because if we were having time, we could have gone for this demo of time history selection. But
Right.
since time is not there, so tomorrow in the demo, we hope that tomorrow we will not have this type of problem of internet. So what you can do is, in the beginning, you can take selection of time histories, and then using the selected time histories, we can demonstrate them, what response we are getting, and how we can compare the response obtained from uh, model analysis using response spectrum, model analysis using time history, and direct time history analysis. So that we can take up tomorrow.
Okay.
So
Uh,
thank you all for joining, for being with us today. Okay, so thank you and see you tomorrow. Tomorrow we will start at 9:30.
right, sir. First lecture will be taken by you on moving